Hey guys, so for Adventure 5 Quest A, I'm going to be going over question 12.1. In this question, we're going to consider an opaque horizontal plate that is well insulated on its backside. The irradiation on the plate is 2500 watts per meter squared, of which 500 watts per meter squared is reflected. The plate is at 227 degrees Celsius and has an emissive power of 1200 watts per meter squared. Air at 120 degrees Celsius flows over the plate with a convective heat transfer coefficient of 15 watts per meter squared Kelvin, and we are asked to determine the emissivity, absorptivity, and radiosity of the plate, as well as the net heat transfer rate per unit area. So I drew a little schematic of what's going on, where we have a block here at 500 Kelvin. There's air flowing over the top of this plate at, at 400 Kelvin with a convective coefficient of 15 watts per meter squared Kelvin. It's insulated on the back plate, and one of the assumptions is that there's uh, no heat transfer or heat loss through the sides. We have an irradiation of 2500 watts per meter squared, where 500 of those are being reflected, as well as a total emissive power of 1200 watts per meter squared. I've organized these so we have our givens here, our assumptions down here, where we have an opaque surface, the transmission is equal to 0, real surface, where the E is some factor away from the emissive power of a black body. We have constant properties, insulated back surface, and heat transfer through the sides of the negligible. And of course, we're being asked to find the emissivity, absorptivity, radiosity, as well as the heat transfer rate per unit area. To do so, we're going to be using this equation to find the emissivity, where we know that the total emissivity, E, divided by the ideal emissivity of a black body, which is defined by the Stefan-Boltzmann constant times temperature to the power of 4, and that gives us an emissivity of 0.34. Now, when we're looking for the absorptivity, we're going to start with the irradiation and say that the reflected, absorbed, and transmitted is all going to be equal to the total irradiation. Now, we know that because we have an opaque surface, the transmitted is equal to 0, and we have the reflected, which is just 500, we were told. Solving this, we get the total absorbed radiation of 2000 watts per meter squared, and using the ratio of the amount absorbed over the total, we get the absorptivity of 0.8. Now, in order to find the radiosity, J, we're going to first start by solving for all of these together, which equals 1. So the absorptivity, the transmission, and rho is equal to 1. Now, that gives us this value is equal to 0.2, and the radiosity is equal to E plus rho G. Solving this equation, we get a radiosity of 1700 watts per meter squared. Now, in order to solve for the net heat transfer rate per unit area, we're going to solve for an energy balance equation where we know that the irradiation minus the radiosity minus the convective force, the convective heat transfer here, is equal to the net heat transfer rate per unit area. We all have all of these variables here, so we plug that in, solving for the convection, which is just equal to the convection coefficient times the difference of temperatures, and we get a Q double prime net of negative 700 watts per meter squared. Now, because it's negative, we know that the net heat transfer is leaving the block itself. So this temperature will be getting colder as it goes to steady state. And that's my solution for question 12.1.